Yeah, let's get started with morning's festivities. My name's Scott Beeson. I'm the park geologist at Mount Rainier Park. I'll be serving as this session's facilitator. So thanks for joining today. I'm really excited about this. Looks like a great session. Lots of really cool talks. Morning session is called Dynamic Earth. The description about it is what's new in Cascade Subduction Zone? What new techniques are improving the ability to predict and detect geologic hazards in our parks? Meanwhile, lidar and other remote sensing technology is revealing information and trends invisible from the ground. And how can these new tools and perspectives inform stewardship priorities? A couple technical notes. Presenters, please use your camera so the audience can see you. My camera will be off during most of the talk, so when it gets down to 1 minute left in the talk, I'll come on and show a little 1 minute thing when you've gone to your end. And hopefully you can leave some time for some good questions and answers. Again, audience, if you have questions, as Hazel mentioned, put them in the Q&A section, and we'll address them at the end. So the first talk today is John Boetsch from North Coast Cascades Inventory and Monitoring Network. It's called Using Machine Learning to Classify Landscape Disturbances in Pacific Northwest National Parks. I'll hand it over to John.
Great, thanks, Scott. Let me share my screen here so I make sure that everything's working. Yeah, these have been great meetings so far, and I really appreciate you and Hazel and everybody who's been involved in this. So can you see my screen then?
Yes.
Okay, great. Greetings, everyone. My name's John Boetsch, and I'm pleased to talk today about some of our ongoing work to monitor disturbance and landscape change using satellite imagery, and I'll be focusing on our recent efforts to make this process more efficient by automating disturbance labeling using machine learning and a random forest classifier. So first, a bit of background. Why are we interested in disturbance? Disturbances are fundamental ecological processes that shape ecosystem structure, composition, character, and function. Climate is a key driver of disturbance that also influences post-disturbance ecosystem recovery through conditions such as excessive precipitation, rain on snow, high wind events, in addition to summertime drought, excessive heat, and insect outbreaks. The list goes on, and all contribute to a dynamic ecosystem in the mountains and riparian corridors of the Pacific Northwest. In an era of rapidly changing climate, it's increasingly important to monitor how these disturbances might be changing at a landscape scale. Here's a short list of the categories we use to classify these disturbances into meaningful groupings, with the recognition that some of these categories may include several agents and represent a combination of factors. Still, we have settled on these as repeatedly identifiable using aerial photography and other validation methods. So to summarize a very complex process in a single sentence, the means for mapping disturbance is to use a series of freely available data, Landsat, which is evaluated using a change detection algorithm to pick up abrupt declines in spectral greenness to produce patches representing disturbance. These patches are importantly unlabeled, however, which means that the resulting disturbance map output can be quite scattered and difficult to interpret, as shown in the map of Mount Rainier on the left. To make this more useful and interpretable has so far required a significant amount of time to eliminate some of the interannual scatter and produce a labeled disturbance map like the one shown on the right. The main question of this project is how can we make this process more efficient so that it doesn't require so much time for human review of each polygon? So the concept was to take advantage of the fact that we now have nearly 30,000 human labeled polygons representing over 30 years of disturbance, um, diligently compiled and curated by none other than our super geographer, Natasha Antonova, and to use that to develop an iterative random forest modeling framework for automating the labeling process, allowing us to more efficiently generate map output. For that, we had the mad coding skills and general brilliance of a scientists in parks intern named Dan Wexler to help out. So here's a quick overview of the workflow we developed. Step one is to start with a large amount of test data using human labeled disturbance polygons. And here's a table showing the distribution of labeled data by disturbance type for the 3 parks we studied. You can see that some of the disturbance types are quite well represented, while others have quite small numbers of disturbance polygons. Step 2 is to calculate predictor variables in GIS for these labeled polygons. And again, here's a table of the broad categories of multiple predictor variables that we used, including spectral data from imagery, landscape terrain variables, polygon shape attributes, and variables to capture additional information about space and time of each disturbance patch. The next step is to reduce the number of variables by eliminating redundancy and low information variables. And here's a heat map of a correlation matrix for one of the predictive variable classes, which we use to interactively eliminate collinear variables from the model predictor set. Next, we get to train the random forest classifier model with this labeled data. And for a quick schematic view of what this random forest model does, here's a decision tree schematic showing how the model splits the data on various combinations of predictor variables to ultimately generate the disturbance type labels. Next, we test the random forest model on data that were withheld from the training data set and generate error matrices like this one, the human labeled disturbance type against the predicted type to see how well the model performed overall for each category. And we found, somewhat unsurprisingly, that for some of the more prevalent disturbance types, the model performed relatively well, but performed poorly for rarer types. Which brought us to the question of whether we could increase overall model performance by setting different confidence thresholds for the various patches. Confidence being a random forest term for the percent of trees that vote for the winning classification. And for brevity, I'll just state that we did find that by setting different confidence thresholds for each disturbance type, we achieved more desirable error rates while still labeling a large set of patches. These results are preliminary, and we still have some additional work to do to finalize the workflow and results. But considering that the main objective of the automated labeling is to reduce the workload required by focusing the model on disturbance types that perform well and leaving the smaller, more poorly predicted categories for continued human review, we're optimistic about our abilities to meet this objective. So the final steps are then to apply the model with its different confidence cutoffs for each disturbance type to new data acquired periodically. To finalize the new map, we plan to flag a percentage of these model labeled disturbance patches and perform human review to determine actual error rates and compare these with the model's expected error rates. We can then later use these new human labeled data to repeat the process, thereby gradually improving model performance and the overall efficiency of our monitoring. So we have some continued work planned to further test this and give it a spin on some 2024 data and then write up results in a publication. More to come on that. To close, I'd just like to acknowledge again the terrific partnerships and contributors that have made this possible over the years, especially my co-authors on this project, Dan Wexler and Natasha Antonova, who are featured on this rock album cover photo on the left. Thanks for your attention.
All right, thank you, John. Great talk. If you have questions, throw them in the Q&A. We'll discuss them at the end. The next talk will be Jose Jimenez from Cal State University San Bernardino, measuring changes in Mount Rainier's debris-covered glaciers. Okay. Jose, it's all yours.
Jose, we can't hear or see you yet.
There we go.
Okay. Jose Jimenez. I'm from California State University of San Bernardino, and today I am presenting measuring changes in Mount Rainier's debris-covered glaciers. So I'm going to be focusing on Emmons Glacier. It's a northeast-facing debris-covered glacier on Mount Rainier. So this is a picture of Mount Rainier, and in light blue, it's Emmons Glacier, whose meltwater flows into the Puyallup watershed via the White River. It's around 11 square kilometers, and around 20% of it, mostly in the lower elevation part, is covered by rock debris. And this significant event from 1963, a small steam explosion around at Little Tahoma Peak, which you can see in black and white in this image, is from 1965. It caused a rock avalanche that put 14 million cubic yards of rock to travel down 4 miles. And now this is the future. This is us hiking down in July of 2023 to do our investigations. So the importance of this is that It's known that debris-covered armoring has slowed glacier thinning. So the rock debris on this glacier is helpful to an extent. But how are we addressing debris cover impact on Emmons Glacier? First of all, I am tracking glacier extents from 1951 to 2023, so manually digitizing the area of Emmons Glacier. Next, I'm also using digital elevation model. This is where I take an old digital elevation model, subtract it from a new digital elevation model, and then we'll see elevations of loss and elevations of gain. Next, we're doing on-site debris thickness measurements, and we're checking how thick the debris cover is until we hit the ice. And this is Angel, an undergraduate from CSUSB also. So first, I'm going to present the glacier extents through time. So this image shows 1951 orthorectified imagery. And in red, it shows the 1951 glacier extents. Next, I'm going to present the next imagery that's available in 1967 that we have. This is the only image that's orthorectified that has the rockfall avalanche that we're able to orthorectify. And we can see that it's slightly.
Sure.
And next is 1951 to 1991. And I'm going to be zooming into this black square right here. So from 1951 to 1967, there's a 2% decrease, like a recession of the glacier. But if we do it from 1951 to 1991, there's actually a 3% advance in the glacier. So then doing glacier extents from 2006 to 2023 using a National Agricultural Imagery Program imagery, we can see, I'm going to zoom into this black square, and this is 2023 imagery. We can see that from 2006 in the red outline to the light green in 2023, there's a yearly 1% decrease. Sometimes it's 2%, but the glacier is receding from this time. Next, I'm presenting the digital elevation model differencing, and you can see that most of it, I have in black the debris cover portion in the upper right, and most of the elevation loss is down the center line of the glacier, and it's lost up to 20 trillion gallons of ice. And yeah, that's kind of sad. But next, we have on-site debris thickness measurements, where in blue, it's places where we hit ice, and then in red, we didn't hit ice, like the pit would have collapsed. And we could interpolate this using ArcGIS to find where exactly the thin debris and thick debris is. And then this image shows an interpolation of all those sites that we dug up. So in red, it's showing thicker debris, and down the center line, it's showing thinner debris. We could also correlate the digital model differencing and what I just showed you, and then it shows that in red, the more negative values, it's showing thin debris plus lots of elevation loss. So to conclude, unfortunately, Emmons Glacier is currently in retreat, but understanding debris thickness patterns helps us predict future glacial morphology, and it can help monitor glacial retreat and the potential downstream impacts of the Puyallup watershed via the White River. And thank you for your time.
All right, perfect. Thank you, Jose. It was exactly 5 minutes. Good job. Next talk will be Dr. Alex Iezzi and Wes Thelen from USGS. I think Alex is the one presenting Unraveling the Details of the 2023 Tahoma Creek Debris Flow with Multidisciplinary Observations. Alex, it's all yours.
Okay, awesome. 1 second, let me just get my screen shared. And I will also preface this by saying I am hotspotting my phone because it's surging due to this storm. So hopefully it goes well. everyone see that?
Okay, I'm not seeing anything, Alex.
My screen was frozen.
Okay, Alex, we're gonna figure out your stuff. We're gonna go to Veronica real quick, and then we'll come back to you, so that's okay.
Yeah, sorry, it logged me off quick, just because the internet keeps flickering.
Okay, so we'll skip around. So we'll come back to you. How's it sound? So Veronica, if you're ready,
Sounds
so Veronica, I'm gonna murder this name. I apologize. Gaete-Elgueta. Hopefully I got that. Apologize if I did. Use of distributed, acoustic, the tool for monitoring geohazards in Mount Rainier. And if you're ready, it's all yours.
Yeah, can you see my screen?
Yep.
Perfect. Okay. Okay. Good. Okay. Hi everybody. So today I'm gonna talk to you about our project called MORADAS, where we use distributed acoustic sensing as a monitoring tool of geohazard at Mount Rainier. I'm Veronica. I'm a PhD student at the University of Washington. And my collaborators are Manuela, Dominic, Marine, and Brad, and other. So here, so we are studying seismicity at Mount Rainier, so we can here see we have a diverse seismicity, so we can find like earthquakes, shallow earthquakes at the summit. We can find a surface event too. We can find like more earthquakes related with the tectonic in the west flank of the volcano. Also, we can see anthropogenic nodes, climbers, ridges, resonance, and others. So what we are doing here is measuring this seismicity with fiber optic cables. So this is like just to illustrate that we have like a fiber cable that is deployed for telecommunication purposes to give internet to Paradise Visitor Center. And so we connect for almost 1 year this interrogator, this machine that is sending a pulse through the fiber. So we can record the strain of this fiber when it's interacting with an acoustic field. So the advantage of this technique of the DAS is then we have a dense spatial resolution. So we are talking here about like meters, 10 meters. And also we have like relative, right, like low cost maintenance for a permanent and continue recording. So this is our cables. This is Paradise Visitor Center in Zero, and the cable is on the road, so it's following all the cars stuff until Ashford. Here we were trying to locate the channel, so where is every part of the cable. And then here we have the seismicity map at Mount Rainier over 1 year. So we have here the west flank that I was telling you about it, more related with the fault over there. And we have here the shallow earthquakes that are also surface event that we are on the summit. So what we are seeing in our DAS data, it's these diagonal lines are car noise, when cars are going up and back. And we can see the Nisqually Bridge here. We record also a snowplow that it was cleaning the snow during the winter time. And because we knew it where was the Nisqually Bridge, we select this specific channel and we calculate their resonance frequency of the bridge, and so we can identify day and night times and stuff like that. Also, we record some volcanic events. So we have here like 2 events. We can see clearly the P and the S wave for 2 volcanic events in the same window. They were located at the summit of the volcano. And here, this is one more related with the west side of the volcano. So this is how earthquakes looks like and in our DAS data. So what we were doing here, it's we were looking for more earthquakes, trying to see with this technology we can find more earthquakes. So we applied template matching. So what we did was taking a template, an earthquake event, and then scan through the continuous data, like doing a cross correlation and find more earthquakes. So what we found here is we found more earthquakes, small earthquakes, sorry. In this section of the channels, also we have an amplification here. So we identified that we could find small earthquakes, more small earthquakes in this area, and we are related this better and sensitivity with the lithology. So probably here we have like bedrock instead of like volcanic rock over Mount Rainier. So we found that we can monitor the seismic event with this and find more earthquakes. And yeah, and we're very excited to present more stuff the next run. That's all. Thank you.
Okay, thank you, Veronica. And there's my timer right there. Okay, we're gonna go on to Manuela and then go back to Dr. Iezzi after Manuela's talk. So the next one will be Manuela Köpfli, excuse me, monitoring near-surface environmental changes at Mount Rainier using distributed acoustic sensing, another DAS talk. So, and Manuela, whenever you're ready, it's all yours.
Do you see full screen?
Yep.
Okay, perfect. So I changed the title slightly. So I want to focus on ground moisture across lithologies at Mount Rainier. And again, that's a collaboration between University of Washington and the Mount Rainier National Park. So if you think about monitoring ground moisture, you might think about ground moisture probes. And in Mount Rainier National Park, there are actually 4 of them currently running. But another method is using satellite measurements. But this also already shows a problem because most of the national park is actually just dark blue of the high, densely vegetated area around Mount Rainier. So we cannot really use the satellite measurements because they don't monitor ground moisture. They're just monitoring the vegetation on top of it. If we now take the ground moisture probes and print the lithologies or the geological map on top of it, we see that each of these ground moisture probes is in a different lithology. So we can compare different lithologies or different ground moistures across different lithologies, but we cannot do any statistics. So it would be neat to have more data within one lithology to apply some statistics. And that's where this new technique comes in, which is located in the black triangle. And you see this map again. So the black line is the cable, the numbers represent the channels, so each measurement point along the fiber, and you see that we cross different lithologies, but we also have many, many measurements within one lithologies, which allows us to do statistic and tackle the question about ground moisture changes across lithologies. So now you might wonder, this is a seismic tool, how do I want to get ground moistures from it? And that's where this autocorrelation method come in. And I want to explain that with this two sketch. So we have a time t1 and a dry subsurface. A seismic wave is traveling through. The subsurface is recorded at the surface by a recorder, and that ends up in this blue signal. Now we autocorrelate it. This means we copy the same signal and correlate it with itself. And this ends up always in a spike at 0 lag. So there we always have 1 because it's exactly the same signal, but to the left and to the right, so with positive and negative lag times, you see that there are much smaller wiggles. If we do that now for a time t2, where it's rainy, the subsurface is wet, we have again a wave traveling through the subsurface recorded at the surface. We record a slightly older signal and do the same process again. So again, autocorrelation. We see that we have still this peak at 0 lag, but to the left and to the right, we have, slightly altered wave field. And that's what we want to use to monitor the subsurface. Now, a different way to represent this autocorrelation is this one. So along X, we still have the lag time, but along Y, we have many, many different autocorrelation functions across different times. And the color represents the amplitude. Now, because I'm more familiar with looking at time series from left to right, we turn the whole thing. So now the first time step is at the left-hand side and the last time step at the right-hand side. And another thing to simplify is removing the lower half of this plot because it's perfectly symmetric. And now we are where we want to be, and we can look at some real data. So these are autocorrelation functions for 3 days. So left-hand side is first day, and then going to 3 days later. And we can use this to actually get something like a stretching. It's kind of control here. Yeah. So which we call DT over T. And what is done here is we take each of this autocorrelation function in the upper plot and compare it, for example, to the first one. And we do this by allowing the correlation functions to be stretched and compressed, and then plot the best fitting factor, so the best, for example, compression factor along the y-axis. And this gives us the scattering along y, and the color is simply how similar are these two functions, the first versus all the others. And if we add now some weather data, which is precipitation per hour in blue and ground moisture at 2 different depths as dashed lines, we see that DT over T and the ground moisture have similar shapes, and we see a drop in the correlation coefficient during increased ground moisture. And with that, I want to sum up and say we can actually use seismic data to estimate ground moisture because we can measure changes in travel time of seismic waves and changes in correlation coefficients. And with that, we can increase the spatial and temporal resolution compared to ground moisture probes and satellite projects. Thank you.
Okay, excellent. Thank you, Manuela. We're going to go back to Dr. Alice Iezzi and Wes Thelen from USGS. I think we've got the technology stuff figured out. Unraveling the details of the 2023 Tahoma Creek debris flow with multidisciplinary observations. Alex, all yours.
Awesome. Thank you, Scott, and thank you everyone for being flexible in this. We had a power surge right as the presentation was starting. So as Scott said, my name is Alex Iezzi, and my co-author is Wes Thelen from the USGS Cascades Volcano Observatory, and in particular, we work on the Rainier Lahar Detection System project. And so today we just wanted to give a few updates on some multidisciplinary observations that we have from the 2023 Tahoma Creek debris flow. So taking a step back, in general, for lahars are one of the most far-reaching and destructive hazards, and in particular at Mount Rainier, this is one of the main hazards that we look for because it's had a history of these very large lahars that can affect areas that are now fairly populated. So a study from 10 years ago, back in 2015, said that there were over 90,000 people that live in Rainier lahar hazard zones. So it's probably quite a few more people now. And at least 11 large lahars have happened that have gone into the Puget Sound lowlands in the past 5,600 years. And so this led to the creation of the Rainier Lahar Detection System. And generally, that goes along with the Rainier monitoring network that we use for general volcano monitoring. But one of the issues that we have for the Rainier project is that recordings of these very large lahars are pretty sparse on modern equipment such as seismometers and infrasound arrays. And so we rely on a lot of things like geologic mapping and modeling, as well as smaller signals that we can see. And one of those is the seasonal debris flows that happen at Mount Rainier. So these smaller debris flows are quite common at Mount Rainier. There's been a few studies on them. At least 33 of them have occurred in the Tahoma Creek, which is shown in the blue box on the right-hand side. And this is what debris flows, and the scour is what caused the once popular West Side Road trailhead to actually be closed. And there was one of these that occurred now a year and a half ago on August 15th, 2023. And it was likely some form of a glacial outburst flood from the South Tahoma Glacier. It occurred late in the afternoon after a couple of days of really hot weather, and it was on a very hot summer day. And so we have quite a few observations from this flow. So to start off with, we have the permanent monitoring network, which is shown in these triangles over here, with the stars being the 4 infrasound arrays, as well as the 10 broadband permanent seismometers that recorded this flow quite well. We also fortuitously had a bunch of campaign equipment out, including 37 seismic nodes, so small seismometers on that Tahoma Creek drain. And we were also testing a laser rangefinder, which I'll talk about in a little bit. We also pulled in data from the Paradise Weather Station, as well as looking at satellite imagery. So here we have a before and an after. To get yourself oriented, if you're familiar with Tahoma Creek, there's a suspension bridge, which is pointed out. And you can see that after the flow, this is about 3 days afterward, That part of the section where we're focusing on became straighter from the increased flow. There was overall higher volume, and there was kind of this new offshoot that happened. So the channel morphology changed quite a bit as a result of this. And finally, we have geologic observations from our awesome friends at the park. So this is from Scott Beeson himself. So within, I think, an hour of the flow, Scott was already up in a helicopter taking photos of the flow and the incision. So these are awesome observations to have. And so one of the things that we were trying to work on is trying to calibrate our permanent monitoring network so that we can use these for these very large lahars. So on the left-hand side, we have the permanent seismometers. So this is just showing an envelope of the amplitude as it moves downstream. And these, quote, seismic nodes that we had 37 of, basically within the distance of maybe like 4 of our permanent sites, we had 37 of these. And so we can really try to unravel those details in the flow and how it changes as it moves down channel, which can then help us work on future debris flows. This also allowed us to kind of calibrate our detection algorithms and tracking capabilities for the Rainier lahars detection problem. So on the left-hand side, you can see our seismic amplitude locations, and this is kind of just showing where the flow was. And on the left-hand side, we have the infrasound array processing, which is the back azimuth, or that direction where that loudest sound is happening. From yellow to black colors, that's kind of just showing the progression through time. So both of these algorithms worked pretty well. And then finally, we started working on the testing of new technology. And so going back to that Tahoma Creek suspension bridge area, we had a laser rangefinder out for the summer, as well as our co-located seismometer and infrasound. And what we can see from these is they track really well. So this is just showing the envelopes, so kind of just those amplitude through time. And a few things that we see are that the seismic and the infrasound have an emergent offset over a couple of minutes. So trying to figure out exactly when the flows showed up at that location is difficult. But the laser rangefinder was showing quite a bit of promise for having this really clear and precise onset for when the flow made it at that point, which is one of those main things that we're trying to figure out from the Rainier lahar detection system so that we can track that flow through time. And so with that, I'll just kind of summarize with saying that there was a small debris flow that occurred about 1.5 years ago, where we had a variety of both permanent instrumentation as well as fortuitously some campaign equipment to observe that flow. And these multidisciplinary observations can help us unravel the flow properties and dynamics in more detail than our permanent monitoring network can do alone. And so this helps us try to figure out the flow properties and be able to better detect these in the future. And yeah, so finally, this just helps us calibrate our system and kind of fine tune our algorithms for the overall Rainier lahar detection system. So thank you.
All right. Thank you, Alex. Great talk. A lot of fun working with you guys on the debris flow stuff.
Yeah, it's been great.
For participants' questions and answers, feel free to add them to the Q&A section in Zoom. We will address those all at the end. Our next speaker is Scott Anderson, talking about erosion of river valleys downstream of retreating glaciers, observations of the Hoh and Puyallup River watersheds. So, Sanderson, it's all yours.
See, you guys are getting there.
And we can see your slides.
Perfect. All right, can you hear me?
Yep.
Cool. All right. Well, thanks, Scott. My name is Scott Anderson. I am a hydrologist with the U.S. Geological Survey in Tacoma. I'm going to be talking here about 2 projects we have going on the Puyallup River and the Hoh River, both of which drain national parks, but more directly, both of which drain glaciated terrain up in the Olympic Mountains and Mount Rainier, respectively. And I'll say right off, a lot of this work is a little bit more about what's happening downstream of the parks as opposed to necessarily in the parks, but hopefully it's all interesting and relevant. So a lot of this work is sort of built along this hypothesis that recent glacier retreat is exposing all of this unstable sediment. You know, the Nisqually Glacier here is kind of emblematic of what we're talking about. That is leading to some sort of increased downstream sediment delivery, and that extra sediment coming from these deglaciated headwaters is essentially overwhelming the river's ability to transport that sediment, leading to sort of channel infilling or aggradation with associated flood hazard or channel migration hazards. So the tool to try to assess this process or this concern is these repeat topographic surveys, mostly repeat aerial lidar, that are allowing us to quantify erosion and deposition in these settings with a fair amount of precision and resolution, both in the rivers as well as the proglacial headwaters. So on the left, a sort of example image of Puyallup River with red showing deposition, blue showing erosion over a period of about 10 years, just showing this river meandering through its valley floor, picking up or eroding material. On the right, we have the Carbon River, showing change over 2 time periods spanning about 30 years, showing debris flow deposited in red on that top panel that was then re-eroded and redeposited a short distance downstream. So emblematic of the kind of data we're using to assess these sediment storage trends throughout these watersheds. And what these all add up to are these sediment budgets that describe the sediment inputs and sediment outputs coming over kind of the full watershed scale. And here the watershed in question is sort of the combined watersheds of the Puyallup River and Carbon River, where they kind of dump into Ording. So we're getting down into the lowlands. And I will say right out that these are total sediment budgets, clay to cobble, so they're not differentiated by grain size. But what we know is that roughly the sediment load exiting these combined watersheds is on the order of 500,000 cubic yards per year. And the question is, okay, where is that coming from? And first off, the dominant source based on what we know in the literature here is probably subglacial erosion. So this is the glaciers eroding right down on the flanks of Mount Rainier and exporting sediment down. The next most significant input, and this is going to be a key point here, is erosion of the main stem river valleys that are linking Mount Rainier to the lowlands. So 2 key points here is that one, the rivers here linking Mount Rainier to the lowlands, what we're seeing at least in the last couple of decades is that they have been eroding more than they have been depositing, so not filling in with sediment, and that they have been doing so at a rate that constitutes a major sediment source or watershed outlets. The next most significant input, at about 12% of the total sediment load, is proglacial erosion, so erosion of those recently deglaciated areas. And then the little sliver remaining up here is essentially everything else. So the 2 key points that come out of the Puyallup River work at the moment are, at watershed scale, when you're getting down to Ording, the proglacial sediment input is not dominant, and that the river valleys, instead of filling in with sediment, have actually been emptying out of sediment at a substantial rate. We're a little early in the work on the Hoh, but the story so far seems to be somewhat similar. We have a rough estimate of the sediment load exiting around Highway 101. And so far what we've seen on repeat topography over the last decade is that basically every reach of the river we've assessed has a negative storage trend, more eroded than deposited. And that when you add it up, it looks like that river erosion is a major, if not essentially dominant source of the total sediment load exiting past Highway 101 here. So kind of brief summary is that from looking at all this repeat topography, the sense is that while there is material being exposed in the headwaters, it's often pretty hard to mobilize it. Material that is mobilized often doesn't go particularly far. And when you zoom out to the full watershed, the net rate of delivery from those areas is not necessarily immense. Somewhat conversely, when the rivers here, what we're seeing is these are acting as substantial sediment sources, primarily through lateral erosion of banks and bluffs. There's a whole lot we don't know. There's a whole lot to be done. But this is sort of where things stand for our understanding at the moment. And I think it's also important to note that a lot of the concerns associated, I think, particularly with aggradation and climate, the bank erosion, larger floods, debris flows, all of these are still essentially just as hazardous as they were before. If they don't necessarily add up to channels filling in with sediment, that may be a distinction with a modest difference in terms of the hazard impacts. So if you want to learn more, we're going to have a report out hopefully on the Puyallup in hopefully a couple of months, and then give us about a year and a half, and hopefully we'll have some papers out on the Hoh River work. Thanks.
All right, there we go. Thank you, Scott. That was exactly 5 minutes. Great job. Again, questions and answers. If you have questions, throw them in the chat, not the chat, the Q&A section. We're going to move on to our next speaker, Dr. Brian Sherrod, USGS, Age and Origin of Low-Lying Coastal Terrace, Olympic National Park, Washington State. And Dr. Sherrod, it's all yours.
You should be able to see my screen now.
Yep.
Perfect.
And we can see your slides.
Great. This is my talk, Age and Origin of a Low-Lying Coastal Terrace along the coast of the Olympic National Park in Washington State. There's a cast of characters there. I'd like to point out that this work would have been impossible without the help of Matt and Gavin from the National Park Service. We'll go ahead and get started here. So on the left is a lidar map of the Olympic National Park, or Olympic Peninsula. The key things to take out of this map are the low-lying brown areas. Those are intertidal and supertidal areas. All of the purple is above, say, 10 meters in elevation. And the area that we're going to be focusing in on this talk are those little green strips along the coast. And those lie between about 5 meters up to about 9 meters in elevation. And we have found that some of these areas are indeed low-lying coastal terraces. And our project is to figure out the age and origin of this terrace. We have 4 main sites that I'm going to talk about today: Ozette River and Ozette. Cape of Lava, there's a small terrace there. And then Sand Point, there's a beautiful terrace at Sand Point. And then we're going to go down to Norwegian Point, which is probably the best example of a low-lying coastal terrace that we have. At each site, we excavated 3 test pits and took samples for radiocarbon, microfossils, and for luminescence age dating. To get at the age and the origin of the terraces. And we use LiDAR maps and RTK GPS, high resolution GPS, to document the terrace elevations. So put this in just to show you what these terraces look like. This is the terrace at the northern end of Norwegian Memorial, just south of the actual memorial. I'm standing on a log taking this picture, looking in to the forest along the terrace surface. You can see on the bottom right of the picture, the bottom right corner is the modern beach surface, and the logs are covering up the modern small sea cliff that's formed there at the uppermost astronomical tides at the site. And then where the blue crate is sitting, the tree-lined surface, that is the terrace surface. It's a relatively flat but sloping surface. It gently slopes from up in this area down towards the beach. And you can see in the very back, this fern-covered area back here, this is the former sea cliff, and the former shoreline angle is back here. And so that's kind of what we're looking at. We're trying to figure out what the age of this surface is and what its origin is. How did it form? You can see in the upper right, there's a typical LiDAR elevation profile, a profile extracted from the LiDAR that shows you what this thing looks like in cross section. So it's a pretty low-lying, flat, gently sloping feature right along the coastline. Here's the model, the conceptual model that we're using, kind of keep in our minds as we go along and start interrogating these terraces and these terrace deposits. This is the modern platform that's forming between Cape of Lava and Sand Point. Sand Point is off in the very far distance there. If you look at the very far bottom right labeled bedrock, that's the planated bedrock surface that's being formed in the lowermost part of the intertidal zone. Mantling that surface is this prominent boulder pavement that you can see lying along the bedrock surface in places. And then in places in the upper part of the intertidal zone, the bedrock surface and the boulder pavement are buried by a sandy beach. Then there's the modern shoreline angle, basically at about the highest astronomical tides. Then above that, you'll find the terraces and the modern sea cliffs. Okay, so that's the model that we're taking into the field to use with us about how these things may form and what we want to look for in the deposits and the topography to give us clues about what the origin is of these features. So let's get started. Here are the sites. I'm just going to step down from Cape of Lava, then to Sand Point, and then end up at Memorial to wrap up the talk. Okay, at Cape of Lava, we have buried tree stumps exposed in the intertidal zone that are about 6,000 years old, give us a really good index of relative sea level. And then at Cape of Lava, we have a buried intertidal platform surface boulder pavement with a terrace surface. And we excavated a test pit into this, and we're waiting for it. Gives us a really good stratigraphy of what the buried, what the terrace deposits look like. If we step down and we look at Sand Point, we see a beautiful glaciated surface that extends down to about modern sea level. We excavated a series of test pits across this and a couple of gouge cores. And the test pits, there's one shown here in the upper right. We have the bedrock surface with the boulder pavement, and then above that we have buried sands with charcoal clasts and intruded roots that yield ages between about 1,600 years ago to about 600 years ago that give us a good idea for the age of the sediments. And then when we go down to Norwegian Memorial down to the south, it's a beautiful platform. There's a beautiful sand spit that extends across the platform. We have a series of test pits that we excavated across this in gouge cores. And the test pits have a beautiful planated bedrock surface with marine deposits that give an age of about 1,600 years for the oldest age of that surface. So our interpretation is that this surface is a marine deposit that has been uplifted and stranded above the highest tides, presumably by tectonic uplift. Thanks.
All right, thank you, Dr. Sherrod. Again, questions and answers put in the chat, or the QA, we'll put them or address them at the end. So our last talk is Dr. Anna Ledetsky from University of Washington, Structure and Properties of the Cascadia Plate Interface, Evidence from a Newly Discovered Exhumed Paleo-Megathrust on the Olympic Subduction Complex. And it's all yours.
Yeah,
we can see your stuff. You're good to go.
Great. Hi, everyone. My name is Anna Ledetsky. I'm a PhD student at the University of Washington. And yeah, today I'll be talking about an exhumed ancient plate boundary fault in the Olympic Mountains. So as we all know, we're located offshore of the Cascadia Subduction Zone, where the Juan de Fuca plate is subducting underneath the North American plate. And these subduction zones are the only settings that are capable of hosting great or larger than magnitude 8.5 earthquakes globally. And where these two plates meet, a pile of sediments known as an accretionary wedge forms. And this is where the actual plate boundary fault that is the source of these earthquakes is hosted. So here at Cascadia, we have a really large sedimentary accretionary wedge, which is exposed only onshore in the Olympic Peninsula. So that's where it's known as the Olympic Subduction Complex. So here on the right, this is a geologic map showing these two units in green, which are these accretionary wedge units. And here, this red triangle is the location of Mount Olympus. And this black line that rings these units is the boundary of this accretionary wedge. So we were interested in knowing whether we can find fossil subduction plate boundary fault zones that once used to host these earthquakes that were then exposed and are now preserved in the Olympic Mountains. So we did years of fieldwork, 3 summers of fieldwork. Our first year, we went to Snow Dome, so here between White and Blue Glacier. And we hiked in along the Hoh River Trail and spent about 3 days sampling in this location. And then the following summer, and then the summer after that as well, we went to Lake of the Gods. So this is located closer to White Glacier, and we helicoptered and stayed for several weeks for each of these times. So yeah, we did a lot of sampling and we did some outcrop photogrammetry and just mapped this whole area. So here's a photo of Lakes of the Gods facing White Glacier, so towards the south. And the first thing we noticed was there's this network of linear parallel fault zones, which are highlighted in yellow here. So these are each of these faults. And I made a geologic map of this area. So each of these faults are these dark black lines here. And there are about 9 or 10 of these linear faults contained in around a 500-meter thickness of deformed rocks. This fabric is really similar to other exposed subduction rocks elsewhere in the world. So we've identified this as sort of a major plate boundary interface, sort of exactly what we were searching for. A fault zone this widespread is likely formed by sort of thousands of earthquakes accumulated over time. So we identify both continuous deformation. This is the deformation that occurs sort of between earthquakes. So this is what would turn sort of bedded sediments you see here on the left into these deformed rocks that you see here on the right, where these beds are broken down into these really small pieces, and these are known as melange. And then we also identify earthquake-related deformation at the micro scale. So these are small images looking at thin slices of these rocks. So here on the left, we can see the breaking of the grains, and they're sort of unoriented and chaotically arranged. And then also on the right, like fracturing of this original rock fabric. And these kinds of rocks are located in these 9 or 10 discrete faults that we identified. So here's an example of one of these faults. The other thing we did was we collected samples from both Snow Dome and Lakes of the Gods. So every sample we took is on this map on the right here. And we measured the maximum subduction temperature for each of these samples. So here on the left, I'm showing those temperatures, and we got temperatures of around 260 to 280 degrees C. So these are consistent with what we call the seismogenic zone, which is the zone that is capable of producing these large earthquakes. So to conclude, our field site in the Olympic Mountains is the only place at the Cascadia Subduction Zone and only one of a handful of places globally where we can actually examine these fault zone processes that produce giant subduction earthquakes in detail.
All right. Thank you, Anna. That was a great talk. That was 8 talks in like very short order. So very, very good job, everyone. If we could have all of the speakers join, turn on their cameras and their audio here, we'll have some questions. Looks like a couple of them are already answered, but I'm going to have the speakers address them again. So this would be, the first one will be for John Boetsch. Any sense why the estimated error in Olympic was higher than for the Cascades?
Yeah, and Ian, I typed the answer in there for you, but in some, basically we've got the errors that are from the different individual classes that are aggregated together, and each threshold we have for the different classes combines those in different ways. So it's not really the final error rates across classes that matters so much. It's hard to compare those because they're going to represent an individual trade-off for each park and for each threshold type. But the main point is there that we're trying to, from a functional standpoint, just trying to label as many of these disturbance areas efficiently as possible, while holding that overall error rate as low as possible. So it's not an overall map accuracy, and to get that final map accuracy, we're going to need to do some additional human review of unlabeled data that was not included in the model development.
Okay. The next question, I think Ian Miller said that was a good answer. This is for Jose. Is there potentially seasonal bias introduced in measuring retreat from photography?
Yes, there is seasonal bias, mostly because like planes can't go over Mount Rainier and be cloudy for like from September to like March. So we need to get like mostly summer orthorectified imagery into ArcGIS, and the only way that I can hand digitize it is through ArcGIS, and then all of that has to be on the same plane, like same geodesic coordinate system, and there's not much available imagery even. And for me to even address the error, like I am hand digitizing it 3 times each, which is like a lot of work to do. And it's taken me an entire summer just to do from 1951 to 2023. And because that's about 91 iterations of hand digitizations, so I could find my error propagation. But yes, there is seasonal bias.
Excellent. Thank you, Jose. This will be for Sanderson. Can you talk a bit about whether you think patterns in the rivers may be related to equilibrium response to past large sediment deposition events, basically the river working through Holocene floodplain?
Yeah, and it's kind of a big open question. I think the short answer is I don't know. It's a very reasonable hypothesis when you go and look at the landscape. There's clearly plenty of sediment left in these valleys from glacial events, lahars. So it's in there, and it's clear the river is reworking some of that. Although a lot of the erosion we are seeing is more erosion of the alluvial deposits, as opposed to just erosion of those sort of Pleistocene, Holocene timescale deposits. All of this, has the caveat that what we have right now are DEMs of difference from about 2004 to 2020. So we have 15 years of observation. So how much this erosion has been going on prior to 2004, so is a bit of an open question.
Okay. Question for Brian Sherrod. I think I need more time with the results. Can you confirm, though, that you ended up with evidence for uplift at Norwegian? Is that you had the date constraints for?
Yeah. And so yeah, I was blowing through things pretty quick when I got to that slide. The test pit 3 at Norwegian Point is really good because where those shells are, they're articulated shells. They're in growth position, and they're also associated with deposits that contain just abundant marine sponge spicules. And so it's a marine deposit, and its elevation is above the highest astronomical tides today, and it dates to about 1600 years ago. The marine reservoir at these sites about 200 years. We've measured that, and so you're looking at a late Holocene, high stand in relative sea level, and one of the easiest ways to do that is by lifting the ground up rather than having sea level go higher. So yeah, we think it's a really good site for uplift.
Cool. We've got a question here from Hazel for Scott Anderson. Do you know the impacts of the Hoh sediment loss infrastructure like bridges on 101 or on salmonids?
Sorry, could you repeat that?
Yep. Do you know the impacts of the Hoh sediment loss on infrastructure like bridges on 101 or on salmonids?
No. Again, sorry. In terms of like what this actually means for like infrastructure and habitat, like that is sort of tack on work to be done. Right now, we're just trying to figure out what those sediment storage trends are.
Okay, perfect. On a question for you from Denise Louie, how do you determine the subduction zone temperatures?
We take little thin sections, little microscope slides of the rock, and we put them under a laser, and it measures the crystallinity of the carbon in it, and that correlates with the temperature of the maximum temperatures that the rocks experienced.
Hey, let's see, any other questions? I'm not seeing any other questions that we have. I'm not seeing anything in the chat or QA. We have a little bit more time. Oh, Denise, it's so cool. Awesome. Okay. The presenters have any questions for each other? No. Follow-up question for Scott Anderson. Are you assuming you're using green lidar?
No, all of this is near-infrared lidar, but there is a process in there, particularly in the lower watersheds, of going through and correcting for different discharges. The distinction being green lidar looks at or tries to look at the channel bottom, whereas near-infrared lidar just gets the water surface. So in theory, there's sort of missing information about what's happening under the channel, although there's a whole process I'm going through of essentially correcting for different discharges in different surveys that I get into nitty-gritty in the report. Gives you essentially a complete reach scale sense of the sediment budget, even if you don't have direct information of what's going on underneath the water surface.
Okay, let's see. Any last questions? One more for Anna. Do you have future study plans in Olympic?
Yeah, we are permitted for more work this summer. We're going to a new site in the Valhalla range where we haven't been before, and we think this feature might be continuous based on the aerial imagery we have. So yeah, hoping that works out well for us.
If there are other questions, you can feel free to email the individual presenters. I don't see any others at the time. So I'm about to hand it over to Hazel here, but thank you again for your participation, I need more coffee, attendance and attention today. It's a great session. I'm really impressed with the quality of the research, especially presenting it in just 5 minutes. So I'd love to hear some of these elaborated a little bit more. I'm looking forward to some of the papers that are going to come out from these. So feel free to collaborate with speakers as you can. Thanks to Hazel and the technical assistance. And remember, we've got another session at 11 o'clock, and I'll let Hazel talk about that here. But thanks for coming, and look forward to seeing the rest of the talks. So Hazel, I'm going to pass it off to you.